Okay, first of all, I want to point out, because I had this comment, and this is actually what I was going to say. Guys, the net change DCA that we have tomorrow makes me a little nervous for this reason. Net change was really focused on in section 8.1. 8.1 is what we covered before spring break. So that would be back on March, whatever that was, 8th. So like a month ago. Okay. So the reason I'm saying that is it's been a long time. And with an entire week off and then a remote week where we did not do chapter 8 stuff because we focused on AP review. And then we've been in the mode of like volume. You have to go back to the beginning of chapter 8. You have to look at your notes. You have to review the assignments. Look back at the beginning of this chapter before you go into this DCA and test. Okay. It is not all volume. Make sure you go back to it. And in true AP style, looking at things with a cumulative view is that this really is kind of a focus on net change here and talking about things that we haven't looked at since like chapter 6. I want to talk some very generals about this trap rule, and then also what we can do if we get into this and kind of just some other related things to part A. I was kind of impressed with the number of people that remember the trap rule or were close to it. But the trap rule only worked if our trapezoids were equally spaced in our picture or in our data. And in this particular one, because the time intervals are equal, we can use the trap rule. It came from the height being the change in your variable, in this case, t. And our height, and it really comes from the interval used and how many trapezoids you're breaking it into. Well, we're breaking this into 10 trapezoids. 10 minus 0 is 10. Divided by the 10 trapezoids is 1 each, which is our change from one piece of data to the next. Okay, so your height would have been 1, and the trap rule says to take your height, to divide that by 2, and then to take the first base plus 2 times the second base plus 2 times the third base plus keep doing that until you get to the second to last base, 2 times the second to last base, and then the last one is by itself, and type all that in your calculator. And I don't remember what this answer is. Um, 1,229.5. Okay, well, trap rule takes a little bit of remembering some specifics, but remember, this was just a fast shortcut of adding up a whole bunch of trapezoids that happen to all have the same height. So here's what my kind of general conversation to you about part A. One of the things I always encouraged you to do in this section was to kind of give yourself a picture of what's going on, just to visualize what was happening. So if I plot a couple points, and I don't have to plot all of them, because I think once you plot a couple, you're going to remember like the little ways we attacked this based on whether we were doing trap rule or LRAM or RRAM or whatever, right? So I have a point at 0, 110. I had a point at 1, 125. 2, 130, right? So if I do a trapezoid, remember our trapezoid has 2 parallel bases. Our height is the perpendicular line that connects those bases, or the distance between those bases. And my trapezoid just then connected all those dots. So I can do each of these 1/2 my height times base 1 plus base 2, right? If either my trapezoids didn't have the same height, or I forgot trap rule and I just needed to go find each trapezoid by itself. And then I would do that again here, is I'd have a base of 125, a base of 130, a height of 1, and we can do this again. 1/2, height of 1, base of 125, and base of 130. The duplication of these inner bases where 125 got used for these 2 trapezoids in a row is why we multiply it by 2. Should say 125, sorry. But that's why we multiply those by 2 on the inside. But remember, our first and last lines drawn only get used for 1 trapezoid, which is why they're in there singly. Okay, so we had trap rule. We also had two other rules in that section, very related, other ways of estimating, actually three others: LRAM, RRAM, and MRAM, right? So just make sure that you go back and review what those are. And so like I could have used LRAM, and remember LRAM says, okay, if this is my base of my rectangle, when we do LRAM, MRAM, RRAM, they're all rectangles, and now it's base times height. And I use the left side of that to create the height of our rectangle. Okay. Any questions on any of that? Now, we also did have kind of a topic in that said, okay, well, what if my function looks like this as it connected those dots? Well, by my trapezoid rule, would my estimate for that be an overestimate or an underestimate? Over, just barely, but over, right? But how about for my LRAM little rectangle that I drew there? If I did my LRAM here, is it an over or an underestimate? Under, right? And remember what we're doing is we're estimating the area under the curve. So that's exactly what this is. It says approximately, we are estimating the integral from 0 to 10 of your rate, right? That's exactly what that is. It's just estimating it instead of using an actual integral to evaluate it, because we don't know the function. We just have some given data. Questions? Okay, so think about what we just found. And this is actually kind of ahead of where we're going to be, because this is really a discussion that happens later on this. But if I were to label this, it says determine approximately, oh, I guess it says in there how many cases of milk were filled. So approximately this many cases. Okay. And then it's asking us to use a table of data. Pay attention to what your data is. This is R of t, and they're asking me to approximate for the derivative of R. When we are given a table of data and asked to approximate the derivative of what we are given, remember that it's going to be your average rate of change that sandwiches this number. So 5.5 would fall right here. I use those two pieces of data in my average rate of change formula, or the slope of the secant line that would go on either side of 5.5, right? So approximating the derivative at 5.5 would be R of 6 minus R of 5 over 6 minus 5. Questions so far? So those numbers are 100 minus 115 over 1, which would be negative 15. And then always labeling the same way we've labeled all year, right? If I just got my answer from a quotient, think about the labels of those numbers in your quotient. R is cases per hour. 6 and 5 are time, which would be per hour, right? Or labeled with hours. And so we have cases per hour divided by hours. This would be cases per hour squared. And so I would say that it is decreasing 15 cases per hour squared at about 5.5 hours. Questions? Okay. Continuing on, and what gets tricky is our table is a rate. Our table is like a derivative of a function, right? Similar to like a velocity. Now, it's not really a situation where we're doing velocity here, but that's kind of what's going on here, is we're looking at the derivative in the table, right? So it says the rate the machine fills cartons was decreasing the fastest. The rate, R of t, is decreasing. It's decreasing, right, when your derivative is negative. So we're talking about the derivative of R of t. And we're talking about when it's actually decreasing, when the slope of that tangent line is a extrema. Minimum, right? Decreasing the fastest. So this is the wrong math word to use here, but the biggest negative number, right? You know what I'm saying? Okay. So the minimum of your derivative. Well, that's where we have to think about extrema, or a minimum of the derivative, right? Decreasing the fastest, which means I had the lowest number, minimum number for a derivative value. Okay, well, extrema of a function happen at critical points of the derivative. Critical points of R double prime is when we have extrema of R prime, right? And critical points happen when that is either equal to 0 or undefined. And I realize now that we really are missing a key phrasing up there, and that is that this is a twice differentiable function, and that's how we would know that it is equal to 0, not undefined. Okay, but underlying concept. So what I noticed is some people were saying that this was equal to 0 because they thought R prime was a number. We don't know what R prime is, right? We plugged in a number and got values like above in part B, but it can be some function, right? All we know is we're looking at an extrema of it, and extremas happen at critical points, and critical points are where it's either going to be 0 or undefined. And so 0. What is the value of the derivative at the extrema? 0. Questions? I should say specifically at 5 here. R double prime at 5 is 0. Okay, explain the meaning, and this is kind of what I glanced over earlier. If we go from 0 to b of R of t dt, the meaning of this is we are finding the area under this. Go back to your labels, guys. Go back to your labels. R of t times dt, the change in time. R of t was labeled as cases per hour, and if we multiply that times time, which is done in hours, we've seen this over and over, right? Which means our integral will spit out the number of cases accumulated from 0 to b. So from the beginning until whatever b is that they ask us to accumulate those cases would be done in something cases. So it is the total, right? We're totaling up the number of cases filled by time equals b. Okay? Use the labels to help you. Similarly, we can help that think through what we're looking at in E. And what we're looking at in E is in a manipulated version of something that we've used multiple times before. Did anyone recognize what's happening with this 1 over b thing? It is. We are used to seeing this more as, you remember this one, 1 over b minus a, from a to b, tells us the average of this function, right? But if a is 0, it is there. B minus 0 is just b. And so what we're looking at is the average of our rate, the average of our cases per hour. Now, let's say I panic and I don't recognize that. Let the labels guide you. B is clearly a time because it came from this interval. And so this would be 1 over something in hours. R of t is in cases per hour. dt is in hours. And so my hours would cancel here, but as I multiply straight across the top, straight across the bottom, that's telling me that my answer to this is still in cases per hour, right? Which is a rate. And that might help a little bit, but you understand that that's what we're finding, right? Is the average of R of t. So it's the average of our rate on the interval from 0 to whatever b is. Questions? So that's our label. It is the average number of cases per hour, the average of our rate, cases per hour, right? The average of our rate for the interval from 0 to b, whatever b is. Other questions?